Hello and welcome to AP Chemistry Review of Topic 7.8 Representations of Equilibrium. In this video, we're going to look at particle diagrams of representations of equilibrium and try to figure out what kind of thinking needs to go into addressing how stresses affect an equilibrium and whether we can look at that qualitatively and quantitatively. So let's go ahead and dive in. We're going to do two practice problems to see the types of problems that might be asked of you for particle diagrams of equilibrium. So the first one, we're going to look at a particle diagram for the reaction between xenon and fluorine gas reacting to form xenon difluoride. And I'm going to represent xenon with these black dots. I'm going to represent fluorine with two open circles bonded to each other, touching each other. And then I'm going to represent xenon difluoride with a xenon atom, a solid circle, bonded to two of the fluorine atoms, which are those open circles. So in my diagram on the left, I have a 1 liter container and it contains at equilibrium some xenon, fluorine, and xenon difluoride. And right now this system is at equilibrium. The question I have for you is if I change the volume of this container to 3 liters, what should happen to the number of particles inside this container? How will they change? And so the first part of a question like this is not to just dive in and start drawing. The first thing you need to identify is what's actually going to happen. So when you look at this equation and you expand the container of these gases, what's going to happen to the equilibrium? And so equilibrium is either going to shift to the right and produce more products, or equilibrium is going to shift from the left and produce more reactants. So the question is, if we expand this container, which way is equilibrium going to shift? If you'll notice, on the left-hand side, we have 2 moles of gases, and on the right side, we have 1 mole of gas. So when you expand the container, is equilibrium going to shift to make less gas, which means it would shift to the right, or is equilibrium going to shift to the left and make more gas? Hopefully, you said that it would shift towards the side that has more moles of gas, in this case, towards the reactants. So the first part of this problem is identifying which way equilibrium is going to shift. The second part is how are we going to represent that? So if we expand the container and equilibrium shifts to the left, the xenon and fluorine that we already have present in the container is not going to change. It's not going to react and produce more of the product. It's going to stay where it is. So according to the law of conservation of mass, if we started off with 3 particles of xenon, we're still going to have those 3 particles of xenon. So I'm going to draw 3 particles of xenon in this container, the 3 that I originally had. Same thing with the fluorine. I have 3 molecules of fluorine, and so according to the law of conservation of mass, I'm still going to have 3 molecules of fluorine. Because the xenon difluoride is going to shift towards the reactant side, some of the xenon difluoride is going to break apart. So we are going to represent that by showing we only have 2 molecules of xenon difluoride here. We're going to break one of those apart into a xenon atom. So I'm going to add another xenon atom because that xenon difluoride broke apart. And then the 2 fluorines are going to form a new fluorine molecule. And so that represents that shift of xenon difluoride breaking apart. We're still going to have some xenon difluoride in there. And again, according to the law of conservation of mass, if we broke one apart, that leaves 1 left over. And so this is one way we could represent the new equilibrium for the reaction of the container expanding into a larger container. For the reaction expanding into a larger container. So hopefully that gives you a way of thinking about how to approach a stress added to a particle diagram and trying to show what would happen to the particles in response to that stress. Let's look at another problem. In this problem, we're going to be a little more quantitative. So in my second problem here, you'll notice that we have some oxygen atoms, 2 oxygen atoms, reacting to form oxygen gas, O2. The oxygen atoms I'm going to represent with a solid dot, and then O2 molecules I'm going to represent as 2 solid dots bonded to each other. In this first diagram on the left, I have a 1 liter container that is at equilibrium. And each particle in here, so that's a particle, that's a particle, that 1 dot is a particle, those 2 dots are a particle. each one of these particles represents 1 mole. So if you'll notice, we have 4 moles of O2 and we have 2 moles of O. The equilibrium constant for this reaction is 1. And again, that's at some temperature. We don't know the temperature, but I'm telling you that the K value is 1. So my question is this. If I add more oxygen atoms, so more O atoms into this container, could this right model represent a new equilibrium after more oxygen was added to the container? And so that's the question we're trying to look at. So let's see how we're going to approach this. So we first need to realize that our K equilibrium constant expression is our products, so the O2 molecules raised to their coefficient power 1, is over the concentration of the oxygen atoms or the reactants raised to their coefficient power, which is 2. So if we look at the number of particles in this 1 liter container, for O2, we have 4 O2 molecules in this container. There's one, there's one, there's one, and there's one. So 4 particles, and each of those particles represents 1 mole. So we have 4 moles in this 1 liter container, meaning that it is a 4 molar O2. We're going to divide that by the concentration of the O, and we have 2 O atoms in here. There's 1 O atom and there's a second O atom. So 2 O atoms in this 1 liter container, meaning that's 2 molar squared. And so you'll see that the K value is indeed 1 based on the concentrations that are in this container. The question is this new container at equilibrium if the K value is 1? So we're going to do the exact same thing. We are going to count particles and see if K is equal to 1. So we're going to look at the O2 particles raised to the first power, and we're going to divide by the O particles raised to the second power. So let's do our counting. So if we count the O2 particles, we have 1 particle, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We have 16 O2 particles in this 1 liter container. So 16 O2 particles means that it is 16 molar O2. Now let's look at the oxygen atoms. We have 1, 2, 3, 4 oxygen atoms in this container. So that means it is 4 molar with respect to oxygen atoms, and then that needs to be squared. So 16 divided by 4 squared is 1. So our K value is indeed 1. So is this box at equilibrium? Is this a possible equilibrium? And the answer is yes, it is, because the ratio of the oxygen molecules, the O2 molecules, to the oxygen atoms squared equals our K value. And that means that it is at equilibrium. So this box does represent our system at equilibrium if more oxygen had been added. These are the types of problems that you're going to need to think about, and the ways you need to think about particle diagrams as they affect equilibrium. You have to count particles, and you have to show the correct ratios, or at least qualitatively, the ratios increasing or decreasing in response to a stress. Hopefully that was a helpful review of particle diagrams and representations of equilibrium. I wish you the best of luck as you study. If you have any questions, let me know. Bye-bye.